Hello, this is the most important video of this course. In this video I will explain the principle of mathematical induction. I will explain why it works and how it works, and at the end of this video I will present our first proof by induction. Let's start. Induction, this is how it works. First, I will start by introducing the implication symbol. Maybe you have seen this symbol before, maybe not. Now it's practical to have this one because it is like a practical thing to have. So this is an implication symbol which can be used in the following way. You can write such a mathematical statement which can be read in many different ways. The first one is simply if x is equal to 2, then x squared is equal to 4. It's obviously true, right? It can be also read in the following way. If the statement x is equal to 2 is true, then also x squared is equal to 4 is true. This is another way of reading the same statement. Or x is equal to 2 implies that x squared is equal to 4. Or you can also say from the statement x is equal to 2 follows that x squared is equal to 4. So these are four ways of reading the same statement. So I hope that you understand what is meant by such a notation. And I will use this symbol in pretty much every video of this course. And in this case, by the way, this can be seen as a statement depending on variable x. So for some numbers, or just for one of them, for x equal to 2, it is a true statement, but for all the other values of x, it will be a false statement. So if x is equal to 4, then this statement is obviously false. Right? And this is another statement, a statement which we can call T2 of x. This is also some statement about number x. And this statement happens to be true for two values of x, because both x equal to 2 and x equal to minus 2 gives a true statement. So now you see also two examples of statements, two more examples. And now I will formulate the principle of mathematical induction, and then I will explain this principle so that you understand the meaning of this principle and that you will also understand that it is a true principle, a valid principle of proving statements. So we start. Suppose that T of n is some statement about a natural number n. If the statement for n equal to 0 is true, and whenever t of n is true, then also t of n plus 1 is true. And what does this mean? This means that for all n, if the statement is true for number n, then it's also true for the next natural number, because you know that n plus 1 is the next natural number after n, right? In natural numbers, we actually have something what can be called the next natural number or a successor. We don't have it for real numbers or for rational numbers, but we do have it for natural numbers, because natural numbers are just constructed in such a way that there is always distance of 1 because between two consecutive numbers. Consecutive means that they come directly after each other. And here is another mathematical symbol. It's A, which is like standing on its head, and this symbol stands for all. So this second statement reads that for all n which are greater than or equal to 0, if t of n is true, then also t of the next number after n is true. So if these two conditions are satisfied, then the statement t of n is true for all natural numbers n. That's it. That's the entire big, magnificent principle of mathematical induction, a very important principle which is a basis for the proofs by induction. So again, if this statement we are talking about happens to be true for 0, and whenever it is true for some natural number, then it's also true for the next number, then we can be sure that it will be true for all natural numbers. And here again, your teacher maybe uses letter P or S instead of T, but the principle will be the same. And now, let's have a look why this principle is meaningful, why it seems sensible to us, or at least I hope. So what do we read here, and how can we see that these two conditions really guarantee that this statement will be true for each and every natural number? Well, let's write down t of 0, t of 1, and so on and so on. So this is the statement for number 0, this is the statement for number 1, and so on and so on. The first condition tells us that t of 0 is true. And this is a so-called base case, which we will always in proofs, we'll have to verify manually by plugging in n equal to 0 in our statement and just verifying that it's really a true statement. Then the second one tells me that whenever t of n is true, then also t of the next one is true. But the first one tells me that t of 0 is true. So I read here, if t of 0 is true, then t of 1 is also true. But now read this statement again with n equal to 1. Now I know that t of 1 is true, and if t of 1 is true, then also t of 2 is true. Read the second statement again with n equal to 2. Then you will get that t of 3 is true, and of 4, and 5, and 6, and so on, and so on, and so on. But of course, you cannot verify all those statements separately, and it is not needed, because this principle guarantees you that if you just verify the first one, the base case, and then you verify the so-called induction step. And what does this mean? If you show that if you assume that t of n is true for some number, and you know that there is some number for which the statement is true because it is guaranteed by the first condition, then also t of n plus 1 will be true if you succeed in proving this induction step. So assume that t of n is true and show that this implies that t of the next number also must be true. Then by the principle of mathematical induction, you will get that the statement is true for each and every natural number. I hope that this convinces you, because you will not get another proof, and I will explain why also. But before I do, you can now understand why this is often compared to the domino effect. So here you see I used n0 instead of 0, because, well, sometimes we will prove some statements which will hold from some point, not for all natural numbers. So if we prove some stating point or base case, and we show that this induction step is true, so if you know that the statement is true for some number, then you can show using this fact that t of n is true, that t of n plus 1 also is true, then you will know that this theorem is true for all the numbers which are greater than or equal to n0. So compare the truthfulness of this first statement as the fact that you that you push the first piece of domino. And here, this one shows that if you push the previous piece, then the next piece will fall. And in this way, if these pieces are standing on the same distance from each other at least, and are as all of the same length, they will guarantee all fall down. So this is the intuition behind. And now, this principle of induction is a part of axioms for natural numbers. And these axioms were formulated by Peano. And here you also have an image from Wikipedia. This image was made by Johann Burckhardt. So this row here represents all the natural numbers, and you see that the row has a starting point but no end point. So this row just continues exactly as the natural numbers do. And the point I'm trying to make now is that axioms or postulates is something in mathematics which you just take for granted. There is some logical explanation for them, but it is nothing you prove. So this is why the only thing you can do is to understand this principle on the level of intuition. And I hope that I succeeded in illustrating this intuition for you. If you want to read more about axioms, you can, or listen more about axioms, you can go to this Pre-Calculus 1 course and watch video 203. And here is just one slide listing the axioms for natural numbers. But now the stuff for this course, which is more practical, how to conduct a proof by induction. So first, you have to write down your thesis clearly. And here you will see that I use some colors, and later I will use the same colors in my iPad in all the proofs, so that you get used to them. I mean, these colors are, these are just colors chosen by me. But I mean, if you, I chose them so that you know that these are some fixed points of the proof. So write down the thesis so that you know what you are doing. Then verify by direct computation the base case. Often it will be t of 0, but sometimes it will be some later natural number. Then write down the thesis for the next number, so next plus n plus 1. And then perform the induction step. And how do we do this? Assume that your thesis is true for some n greater than or equal to our starting point, and verify that this is true means that also the thesis for n plus 1 is true. And this is called then induction assumption, that t of n is true, and this item here on the list gets a star because this is the most intensive part of the proof. The entire rest is easy. This one is often difficult, or I mean, it is the most difficult part of the proofs. But I have chosen proofs which are not so difficult, so we will manage. But I mean, generally, this is the most demanding part. And at the end, formulate the conclusion. Say that according to the principle of mathematical induction, the statement t of n is true for all n which are greater than or equal to our starting point n0. So this is what we are going to do. So this computation, verifying the base case, is very concrete. You simply take the number 0 or 1 or whatever the starting point is, and you verify that this is a true statement. And this is always very easy. But this one is, the induction step is both abstract and more demanding, because here you have to take some n So it will be kind of abstract. You will not get a numerical value. You will just get some expression, probably. And then you have to use the fact that this expression is a kind of true statement and forms a true statement. And you have to show that this leads to the fact that the statement for the next number n is also true. So this one is easy, this one is always more difficult, and you will see several examples of proofs. And the first one is already here. So here we have to prove the following. We have to prove by induction that for each positive natural number n, we have this formula which telling us that the sum of n first natural numbers starting from 1, well, we could start from 0, but it wouldn't change the sum, right, is equal to this expression. And you see that I have written on my iPad t of n in green, so you see how t of n looks. And here, because it is our first proof, I will write clearly how t of 1 will look. You see that this left-hand side here is n numbers. So if I have t of 1, I will just have one number, right? And at the right-hand side, we have an expression which is depending on n. So it is n times n plus 1 divided by 2, right? This is our t of 1. What is t of 2? Generally, you don't have to do this. I'm just trying to make you comfortable with this kind of expressions. So what will be t of 2? Then you have to plug in n equal to 2. At the left-hand side, you will have just 1 plus 2, right? 1 plus 2. And at the right-hand side, you have 2 times 2 plus 1. You see what I'm doing, right? I'm plugging in, instead of n, 2. If I had more numbers n in my formula, I would have to plug in 2 instead of all of them. So this is how this thesis t of n looks for n equal to 1 and n equal to 2. Okay, so now we can start conducting the proof. And now it's time to verify the base case, right? T of 1. And t of 1, I have already written it here, right? But I have prepared some space here for t of 1, so I will write it here. T of 1 tells us that 1 is equal to 1 times 1 plus 1 divided by 2. Is it a true statement? What is the left-hand side? What is the left-hand side? It is simply 1, right? And what is the right-hand side of this statement here? It is 1 times 2, it is 2, divided by 2 is 1. So they are definitely the same, right? So here the statement is true. And in this way we have verified the base case. Our statement is true for n equal to 1. And now we are supposed to write the statement for the next number after n. How will this one look? Well, it is 1 plus 2 plus, and here we have to take the sum of the first n plus 1 positive natural numbers, right? So here behind n we will just add n plus 1. This is the left-hand side of the expression which is defining our t of n plus 1, right? And the right-hand side, you see, I now have to plug in n plus 1 instead of n in this expression. So what will I get? First n plus 1, and then n plus 1 plus 1, which is simply n plus 2. N plus 2. So this is my statement t of n plus 1. And now it is the most important part, because now I have to perform the induction step. I have to show that for all natural n which are greater than or equal to 1, from the fact that t of n is true, also follows that also t of n plus 1 is true. So now I will assume that for some n, this statement is true, and I must show that this means that also this statement is true, right? So I will write it down here. Assume that I will maybe, no, I simply have this t of n there upstairs, so I can point at it. That t of n is true for some n which is greater than or equal to 1. We know that at least for n equal to 1, this statement is true because we have verified t of 1. So now I will mark it by the same green color so that you know that it's the statement above on the iPad, which is true by assumption. So this is our induction assumption. We will show that this implies that also t of n plus 1 is true. And what is t of n plus 1? This is this orange written statement, right? And now, look at this. I will write down one more time t of n plus 1 here. This is the left-hand side of t of n plus 1, and this should be equal to n plus 1, n plus 2 divided by 2. But by now, it is still a question mark. We don't know it yet, right? But we do have an induction assumption which tells us that the sum of 1 plus 2 plus n is equal to, by this green formula, because now we suppose that our formula is true for some n, and this means that this sum is equal to n times n plus 1 divided by 2. This we know by induction assumption, right? We know this from the induction assumption. But from this point it is easy. So now we can use this assumption in order to show that this orange formula is true. Well, let's verify if it is really true. So compute the following. N times n plus 1 divided by 2, which is by induction assumption the sum for all the natural numbers from 1 to n, plus the next one, which is n plus 1, is equal to. And now we have to add these two expressions to each other. And you know that adding expressions is the same as adding just regular fractions. So we have to find a common denominator, which is of course 2, right? We have denominator 2 in this first fraction. And in this second number we have no denominator. Well, but we can create it, right? By multiplying our number by 2 and divided it by 2. It is the same, it is still n plus 1, right? But now we can put together these two fractions. And from the first fraction here, we will have, we will have n times n plus 1. And from the second fraction, we will have 2 times n plus 1, right? And now we see that we got a common factor in both terms which are in the numerator. This is a common factor. So I can factor out this common factor. It is n plus 1, and in my parentheses, so this is my common factor, and in the parentheses I will first get n from the first parentheses, and from the first term, and from the second one I will get plus 2, right? And now I look at this and I see that I got exactly the same result as I was supposed to get. So now I have shown that indeed, if the statement t of n is true for some n, then it must be true for the next one, for the next number, which is n plus 1. And this means that according to the principle of mathematical induction, t of n is true for all n in t, which are positive natural numbers. So we are done here. And just one more thing I wanted to show you. Sometimes you use this sigma notation, and sigma is standing for sum. So this means the sum of all the numbers k with k from 1 to n. So in order to write down what it means, so this is a short notation for the same as here, for this left-hand side. And how do we use it? Well, if we have to sum elements which are called k, and k vary from 1 to n, then we write first the first of them. It will be the starting point, it is 1, and then we have to add the next one. The next k after 1 will be 2, then 3, and so on, until the last one, which is n. So this is a short notation for a sum of, in this case, n numbers. We kind of make a variable out of this term which is being added, and we make it into index, which is changing from 1 to n, and one step at a time. So this is just a Greek letter sigma, and it is a short notation for a sum. Okay, so now you have seen your first proof by induction, and by this you have the formula for the sum of natural numbers from 1 to n. You know that this sum is expressed in this way. Thank you for watching. Bye-bye.